Hi, Assalamualaikum. Good morning. We meet again. This is my lecture 8 of CHM 577, and this is continuing on my lecture of 7 previously. Okay, for lecture 8, I'm going to be talking about the modes of overlap of orbitals. Yeah, everybody understand already now that when two atoms um, are making a chemical bond, the orbitals will overlap. Yeah. And depending on what type of overlap happens, you are going to get different types of bonds being formed. Okay. So I'm going to talk about the first type, which is a sigma bond. Sigma bond. And a sigma bond is formed through head-to-head overlap of two orbitals. So when you see, for example, here, two s orbitals, this is one s orbital on the left, on the right, and another s orbital on the left. When they overlap, obviously a sphere, a sphere, when they overlap, is always head-to-head because it's a sphere, whichever way. So the overlapping orbitals will have their lobes pointing towards each other, and the electron density is concentrated along the internuclear axis. So these are the nuclei, one nucleus there and another nucleus there. So you get the two nuclei of the two atoms, and when they are making a sigma bond through head-to-head overlap, the electron density of these two atoms that have bonded will be concentrated along the internuclear axis. So this example A is what you get when you are overlapping two s orbitals. Now, what about when you are overlapping p orbitals? Now, as you know that p orbitals, you have px, and then you have pz, and you have py, or something like that. Yeah, you have px, py, and pz. Now I'm going to start talking about px first. Now px, it's on, as you already know, axis. Usually we take arbitrarily x-axis is on this horizontal situation like that. So your px will be one px on the left here and one px on the right. When they overlap, they're going to have their lobes pointing towards each other. When they have lobes pointing towards each other, that means they are overlapping head to head, and they're going to make a sigma bond. Yep, so this is the sigma bond that is formed when two px orbitals overlap. Now, as you can see, these two lobes are combining to make one big fat lobe in the middle of your what looks like a little sweet um, to me. And then these lobes on the outside become smaller. They become smaller because the nature of sigma bond is having electron density to be concentrated along the internuclear axis. So this is the shape of your sigma bond that is produced when two px orbitals overlap. And you can also have overlap of two hybrid orbitals, not only atomic orbitals, but hybrid orbitals can also overlap. And this is an example of probably an sp. Yeah, this hybrid orbital overlapping with that hybrid orbital, you get a sigma bond also through the overlap of hybrid orbitals. So that is about sigma bond. So let's have a look at the next slide. A single bond between two atoms is always a sigma bond first. Yeah, when you have two atoms making a bond, the first bond that is formed is always a sigma bond. Yeah, for example, when carbon is bonded to another carbon, it will always be overlapping of head to head first. because this will be the orbitals that will meet first. The other orbitals will be probably situated in this situation or in that situation, but those that are having their lobes pointed towards each other will overlap first, and though that is the bond that is going to be formed first. So a sigma bond will be the first bond and the single bond. Yeah. So this carbon, when it is making a bond with the second carbon, you're gonna have a overlap. This, it looks like to me sp3. Do you recall my hybridization lecture in lecture 7? Look at this carbon atom. You have one lobe, 2, 3, and 4. What has 4 lobes? What kind of hybridization? Is going to have to be sp3. So this carbon with sp3 hybrid orbital, that carbon with sp3 hybrid orbital, the sp3 are going to overlap with one another, lobe to lobe, head to head, and the bond is going to be a sigma bond. And this carbon has one lobe at the top, which is overlapping with the atomic orbital of the hydrogen. Again, lobes pointing to each other. So this carbon to hydrogen is also a sigma bond. Similarly, carbon to that hydrogen, another sigma bond and another sigma bond to that. So you have on the left of your molecule 3CH sigma bond. On the right of the molecule 3CH sigma bond, and between the two carbons, one sigma bond. So what is this molecule? It is actually an ethane. Yep, it is an ethane, C2H6. Yeah. So this is how ethane molecule is formed. Yeah, this is how ethane molecule is formed. You just look at the each center carbon on the left and each center carbon on the right, and you determine the hybridization of that carbon, and then you see how the hybrid orbitals overlap with each other or hybrid orbitals overlap with the atomic orbital. So that is a very, very simple example of formation of 7 sigma bond. One, there's one here, 2, and then 3, and the fourth one between the two carbons, and then 3 more on the right. So that is 4 plus 3, 7. 7 sigma bonds. Right, let's have a look at pi bond. Everybody has heard about pi bond. Pi bond is formed also through overlap, but different nature, different mode of overlap. It is through the side to side, not head to head, not head to head. It's side to side overlap of two orbitals. Now, the overlapping orbitals are parallel to one another. They're not like the sigma. If you recall, the sigma bond is when the lobes are pointing towards each other, but for pi bond, the overlapping orbitals are parallel to one another. So look at this, for example, the 2py, if you like, it can be also 2pz, yeah? This 2py and that 2py, they are parallel to one another. They don't have their lobes pointing at each other. So when they do overlap, they are overlapping side to side. And when they do overlap side to side, they produce a pi bond. They produce pi bond. And this is the shape of pi bonds where the electron density is concentrated above and below the internuclear axis. So you can imagine that there are two nuclei. Oh, let me do that here. Do that here. Okay, I have drawn the nuclei, the dot there, the dot. So you're going to have the electron density concentrated above and below the internuclear axis and away from the uh, the area between the two nuclei. Okay, so when you have 2py um, mixing or overlapping with another 2py, you have a bonding situation, and that will have a shape like this, and you have an anti-bonding situation which will have a shape like this. So don't worry about the bonding and anti-bonding. You're going to be introduced to the bonding and anti-bonding overlap when you do your next code of inorganic chemistry. Yeah, don't worry. And then I'm going to go next into the next slide is to show you the pi bond in ethylene or in ethene. Ethene has an old name of ethylene, where the shape of the molecule has to do with the orbitals of carbon. Okay, you recall that pi bond is from side to side overlap. So have a look at this CHH and another CHH. If you look at that shape, you are going to immediately recognize that it is each one of the carbon is square planar. No, not square planar, trigonal planar. You are going to immediately recognize that each one of this carbon, that carbon and that carbon, they are both trigonal planar. And going into your previous understanding of hybridization, excuse me, trigonal planar is Sp2 hybridization. Now, Sp2 hybridization, when the Sp2 of this carbon overlap with Sp2 of that carbon is going to make a sigma bond. Yes, because the Sp2 is pointing that way, they're going to make head-to-head overlap, sigma bond. Similarly, when the Sp2 of this carbon with the hydrogen, 4 of them, 1, 2, 3, and 4, those are all sigma bonds, the one that are drawn as black or gray stick. However, you have you remember Sp2, you have one unhybridized PZ orbital. Let me have a look at Sp2. Where is it? Yeah, this one. Yeah, Sp2, you have like that. Imagine that is your carbon and your hydrogen, and then there's another into another carbon. You have the 2py, this one here, the unhybridized. So this 2py, excuse me, oh, yeah, overshot. These 2py that are parallel to one another, they are going to also overlap, but they're overlapping side to side. When they overlap side to side, they're going to make a pi bond. And when these have made pi bonds, it's going to have cloud of electron on top and below that sigma bond. Then you have a double bond. So you have one sigma bond, and the second bond between the carbons the second bond between the two carbons is a pi bond. So you have sigma bond and a pi bond. So you have a double bond. So that is why you get ethene or ethylene. Yeah, and this is the shape. This is the shape of your or the drawing of the electron distribution around an ethene molecule. Yeah, pi bond. Yeah, this is it. So you have carbon, Sp2, carbon, Sp2. When the two Sp2 hybrid orbitals overlap, make a sigma. This is a sigma, 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 and sigma. But this 2pz or probably 2py, because they are actually interchangeable. You can, some textbooks refer to them as 2py, some textbooks refer to them as 2pz. Right, when these parallel p orbitals are overlapping, they're going to make a pi bond, and the yellow cloud that you see here, that is representing one pi bond. The top and the bottom representing one pi bond. So you have a double bond between these two ethene, these two carbons, sorry. And that's how it looks like. Again, the representation. You have a sigma bonds and you have a pi bond like that. And it is represented through a double bond. Yep. And this here is about uh, um, the mechanism of hybridization for Sp. Yeah? So as you can recall, you have for carbon is 2s2 2p p2. Yep. When they hybridize, yeah, 2s2 2p2, then one of these paired electrons will be promoted to this empty one. So you're going to have a promotion of electron. This is another way of representing how hybridization occurs. This is your ground state. The ground state of 2s2 2p2, and then one of these electrons is going to be promoted here. You get each of these orbitals S and the 3p's are mixing or hybridizing. So you get, if you need only sp hybridization, this is what's going to happen. This is sp with each one of these, whereas your 2py will have one electron and your 2pz will have another electron. Yep. So I don't know. Yeah, this is the introduction to your ethine. Ethine is when you have your sp carbon bonding with another sp carbon. You get a sigma bond between the two carbon there. But looking at this, you have two electrons, each one in the unhybridized 2py and 2pz. So this is for one carbon, and if you recall, there's one 2py here, there's one 2pz here, and on the right of that molecule also similar thing happened. So 2pz will overlap with the 2pz to make a pi bond because they are parallel to one another, and the 2py will overlap with the 2py to make another pi bond. So what eventually you're going to get is two pi bonds. So you have one sigma bond through this mechanism. Yeah, one sigma bond there, through there. But in here, you're going to have two pi bonds. So for ethine, you have triple bond between two carbons. And it is a linear shape. Why linear shape? Because it's sp. Sp hybridization. So that is the story about the overlapping of orbitals to make ethine. Yeah. So questions that can arise from this kind of discussion is, this is an example. You can be asked how many sigma and pi bonds are present in acetic acid or vinegar molecule. Everybody knows, any chemist will know that acetic acid is CH3COOH. Yep. So if you draw your Lewis diagram, you're going to find that you are going to end up having this this shape where the first carbon is sp3 hybridized, whereas the second carbon is sp2 hybridized. Yep. And then your oxygen here will be sp3, but one of them is two of them are lone pairs of electrons and the other two are bonded pair. So when you draw your Lewis structure correctly, you're going to be able to determine that for this molecule of vinegar, you have 6 plus 1. So 1, 2, 3, 4, 5, and 6. Those are sure to be sigma bond. One of these double bonds is a sigma bond. So 6 plus 1, you have 7 sigma bond. And the second bond for CO is a pi bond. So you have 1 pi bond and 7 sigma bond. And that is the type of question that can arise. And for you to be able to answer this type of question correctly, you have to be able to draw Lewis structure properly. Yeah, Lewis structure properly. And then through that, we can determine what is the hybridization of each of your central atoms. Looking at this central atom, you see 4 bonds. It has to be sp3. Looking at that central atom, you see 3 atoms bonded to it. 1 atom, 2 atoms, 3 atoms. So it has to be sp2. Yeah. And then that over there, you have 4 pairs of, 2 lone pairs of electrons and 2 atoms bonded. So that makes 4. 4 is sp3. Yeah. A single bond is always made up of 1 sigma. A double bond always have 1 sigma and 1 pi to make up the second one. And a triple bond is 1 sigma with 2 pi bonds. Right. So there is a question here where if you're requested or you are required to describe the bond in molecules, you can be given this. Describe the types of bonds and orbitals in acetone. So acetone is CH3 twice and CO. So first of all, you have to be able to draw your Lewis diagram. When you draw your Lewis diagram correctly, you're going to end up having this drawing. And we're going to have probably practice doing that, yeah, Lewis diagram of acetone. And look at this carbon that I highlighted yellow. How many atoms are bonded to this particular carbon on the left? So you can count 1, 2, 3, and 4. 4 atoms, so this particular carbon has to be sp3 hybridized. What about this carbon right in the middle? How many atoms are bonded to it? So you have 1 atom, 2 atom, 3 atom. So you have sp2 hybridization. And looking at the carbon on the right, similar to the carbon on the left, is sp3. But tell me about the oxygen at the top. The oxygen at the top, what kind of hybridization is that oxygen? You just need to determine, remember my lecture from previously, how many lone pairs of electrons and how many atoms bonded to it. So you see here there are 2 lone pairs of electrons and 1 atom bonded to that oxygen. So you have 2 plus 1, 3. 3 has to be sp2. sp2. So sp2. So your oxygen here is an sp2. It's not sp3. No, this is wrong. This is sp2 hybridized. Yep. Yeah, even that's sp2. So when you draw like that, this is how you draw sp3 carbon. This is how you draw sp2 carbon. This is how you draw sp3 carbon. And that is how you draw sp2 oxygen and the overlap of those orbitals. So this has hydrogen attached to it, hydrogen and hydrogen. Similarly on the right, 3 hydrogens, and the sp3 of the carbon on the left and sp2 of the carbon in the middle, they're going to overlap to make a sigma bond between the 2 carbons. Similarly on the right, and like so. So you are going to be able to draw very, very nicely. Oops, I don't know. Yeah, you can draw that. If you understand this diagram, then you're fine. You are extremely fine. If you don't understand, please ask me when you meet me next. And how many sigma bonds are there? How many sigma bonds are there in this molecule? So you're going to say 1, 2, 3, 4, 5, 6, 7, 8. and 9 sigma bonds. And how many pi bond? Only one. There's only one pi bond because pi bond only exists if there is a double or triple bond. Yep. Use the Lewis structure to ascertain the arrangement of groups and shape at each central atom. Postulate the hybrid orbitals, taking note of the multiple bonds and their orbital overlap. So this is the solution. This is how you describe the types of bonds and orbitals in acetone. And that is a question for you. This is a previous question from paper. Given the following species, SO2, SF4, and CO minus, first you must draw the Lewis structure and predict the molecular geometry of SO2 and SF4. This is really very easy to do. You have done this before. Lewis structure is quite simple. Number 2, for the cyanate ion and CO minus, draw all the resonance forms and use formal charges to determine the most plausible. Remember about formal charges, you might be getting more than one possible, but look at the most probable. And then number 3, state the hybridization of the central atom of each of the species above. And this question, you need to get it answered, and we will discuss later in class. If I forget to discuss this, you remind me, because you are going to be learning whether your answers are correct or not. I have the answer, but I'm going to let you do the trying first. You try to answer. Next, you have another exercise for this molecule. This is a huge molecule, comparatively huge, not too big, but it's quite big compared to what we've discussed before. Determine how many sigma and pi bonds in this molecule, and determine the hybridization of C prime, C double prime, and an O prime. So you have to determine what is the hybridization of C prime, C double prime, N, and O. Yeah. How are you going to do that? You can discuss among yourself and give me the answer, and I am going to tell you whether you have answered it correctly. Yeah. And the next question is, if a molecule MX3 has zero dipole moment, when it is zero dipole moment, that means it is non-polar. Yeah, zero dipole moment makes a non-polar molecule. The sigma bonding orbitals used by M, yeah, M is your central atom, which has atomic number bigger than 21. Determine which one is the correct answer, A, B, C, or D. Yeah. So with the information given, MX3, zero dipole moment, what kind of geometry will give you zero dipole moment with MX3, then you determine which hybridization is correct for your M. Yeah. Right. So that wraps up my lecture for this particular topic of hybridization and types of bonding. So there is an answer here which I can give you, but not yet. You need to try it, and we're going to discuss this. Again, please remind me if I forget to discuss. It's only going to benefit you if you remind me. If I forget, then I'm fine, but you're going to be always asking yourself whether you have got the right answer or not. So, okay, kiddies, that's all for my lecture number 8. I'm going to see you in my lecture number 9 in a different topic. In the meantime, try all the exercises that I've given you in here, and then we'll discuss it. Keep safe, everyone, and take care. Bye-bye. Assalamualaikum.